Morning, students. Yesterday we discussed about the crystal lattice points and different types of unit cells, and also we calculated the number of particles present in different cubic unit cells. Now today we are discussing about a very important concept in solid state, that is packing efficiency. Students, here before I calculate the packing efficiency of different unit cells, let me define the meaning of this word, packing efficiency. This is the total space occupied by the particles in a unit cell. The percentage of total space occupied by the particles in a unit cell, that is called packing efficiency. And you can write this packing efficiency as P dot E is equals to is the fraction of or packing fraction is multiplied with 100 where packing fraction is the total space occupied by the particles in a unit cell, and when it is multiplied with 100 we get a packing efficiency. So packing efficiency is the percentage of the total space occupied by the particles. And students, this packing efficiency of different unit cell is calculated by using the formula, that is the packing efficiency is equals to the total volume of all the particles in a unit cell divided by the volume of unit cell into 100. So this is a formula which is used to calculate the packing efficiency of different unit cells. Now let me begin with the first unit cell, that is a simple cubic unit cell. We calculate the total percentage of the particles occupied in a simple cubic cell. So here writing the in short packing efficiency in simple cubic cell as in SSC unit cell. And students, here in simple cubic unit cell, we know that all the particles are present at the corners of the cube, and these corner particles are arranged in such a way that the corner particles are in touch with each other. For example, two corner particles, let me say this is the one corner particle and this is another one corner particle of the cube. So this is the cube. So here these corner particles are in touch with each other. Okay. So with that concept, let me calculate the packing efficiency. So we know the formula to calculate the packing efficiency. The packing efficiency is the volume of the particles in unit cell, so divided by the volume of unit cell. Now students, to calculate the volume of the unit cell in particles, so volume of all the particles in the unit cell, so in volume of all the particles in unit cell and divided by volume of unit cell. Okay, to calculate this volume of unit cell and the numerator term, that is the volume of all the particles, let me define some terms like H length of the unit cell as A, and radius of the sphere radius of atom, or I'm defining here atom as a sphere, so radius of each sphere as an r. Okay. Therefore, in simple cubic unit cell, the relationship between the edge length and radius, first let me define the relationship between these two, then I will go for the calculating volume of unit cell, then I calculate the volume of all the particles in unit cell, and then I will substitute in this formula. Okay. Then finally I calculate the packing efficiency. Say friends, here in simple cubic unit cell, the corner particles are in touch with each other. Therefore, the edge length, this is the A, and the radius of sphere, this is the radius of an atom, and this is the radius of another atom, because the radius of sphere, they are related as. Okay. So the relationship between A and R is, so here H length is equals to, it is R plus R 2R, or we can write R is equals to A by 2. This is the relationship between the edge length and the radius of sphere. Now, I will calculate the first volume of unit cell. Let me write the first point, the volume of unit cell, the denominator term. And since volume of unit cell is, our unit cell is in a cube. We know that for a cube, the length, breadth and height are same. Okay. And volume of that cube is nothing but it is a length into breadth into height. You can write length is also A, breadth is also A, and height is also A. Therefore, A cube is the volume of unit cell. Now, let me express this volume of unit cell in terms of radius of sphere. Okay. For that, I will substitute A value as 2R. Therefore, 2R whole raised to cube. So that is equals to 2 cube is 8, and this is R cube. So 8R cube is the volume of unit cell in terms of radius of a sphere. Now friends, similarly, let me calculate the volume of all the particles in the unit cell. So here I am doing that work. Thus, let me put this as in 1 and this one as in a second. This is the numerator term. So volume of all the particles. Now friends, the particles we consider as in a sphere. So volume of each sphere, we know the volume of each sphere is 4 by 3 pi r cube. Let me write the volume of all particles in SC unit cell, that is simple cubic unit cell, is equals to, so volume of each particle is 4 by 3 pi r cube, because the particle is considered as a sphere, and the total number of particles present in simple cubic cell is 1. Therefore, we write 1 into 4 by 3 pi r cube is the total volume of all the particles in simple cubic cell. We also write the formula for this numerator term as the number of particles is multiplied with volume of each sphere. That will give me the total volume of the particles present in the simple cubic cell. Now, we got the volume of all the particles and also the volume of unit cell. Substitute these two values in the formula and you will get the percentage of the total space occupied by the particles. So therefore, packing efficiency is equals to, in numerator it is 4 by 3 pi r cube divided by volume of unit cell is 8r cube, 8r cube into 100. So here r cube cancels. So 4 ones are 4 twos are 8. So in numerator the terms remain here pi, only the pi is remaining, and 3 comes to denominator. So this 3 and into 2 is 6 into 100. So pi value we know it is 3.142 divided by 6 into 100. If we divide 3.142 divided by 6, we get the 0.524 into 100. So and multiply with 100, so we get the 52.4%. Okay, so 52.4% is the packing efficiency in simple cubic unit cell. Okay. Okay, students, let me repeat the steps in calculating packing efficiency in simple cubic unit cell. Okay, while deriving or while calculating the packing efficiency, the steps are: first you have to define the edge length and the radius of a sphere as A and R respectively. Then you draw a simple cube, you have to show that there are two corner spheres, they are in touch with each other, and define here R as radius of sphere and edge length as an A. Then write the formula to calculate the packing efficiency. Then derive the relationship between edge length and R. Okay, the edge length and R is for simple cubic cell is A equal to 2R, or R equal to A by 2. Okay. Then calculate the volume of unit cell. First calculate the denominator term, volume of unit cell. That is for cube, it is always A cube. So volume of unit cell is A cube for all type of the packing efficiencies, and express this volume of unit cell in terms of radius of a sphere as A, replace that by 2R, because we know the relationship between edge length and R is A is equals to 2R. So here replace A by 2R, so 2R cube is 8R cube. After this, then go for numerator term. So in numerator, volume of all the particles. So volume of all the particles in simple cubic unit cell or in any unit cell is defined as number of particles multiplied with volume of each sphere. Okay. So the total number of particles in simple cubic unit cell is already calculated, is 1, and volume of each sphere is 4 by 3 pi r cube. Okay. Now substitute these two values in this above formula. Okay. So there is, here I am writing that word, so that is packing efficiency is equals to 4 by 3 pi r cube numerator divided by 8 r cube. Then after simplifying this, you will get 52.4. So 52.4% means it is the total space occupied by the particles in simple cubic cell. Okay, students, the next one is the packing efficiency in face-centered cubic unit cell. That is the FCC unit cell. And the same method we follow to calculate the packing efficiency in hexagonal closed packed structures and also in cubic closed packed structures. So these are the different closed packing arrangement of the atoms. So that is HCP and CCP. We study about this later. So here HCP closed packing arrangement and CCP closed packing arrangement or structures have a unit cell of FCC type. So that's why we apply same method for HCP and CCP structures and also for FCC unit cell. Now students, let me calculate the packing efficiency in FCC unit cell. And students, here in face-centered cubic unit cell, the face-centered particle and diagonally opposite corner particles, they are in touch with each other. Okay, we select those particles to calculate the packing efficiency. Okay. So first let me draw the arrangement of particles in FCC. Okay, before that we consider the edge length as A and radius of sphere or radius of each atom that is considered as sphere is equals to R. And here the let me take the three particles diagonally opposite corner particles and one face center particles. Let me select, this is the one particle here, and diagonally opposite particle means this one. So these are the diagonally opposite particles and face center particles is here. So these particles are in touch with each other. Okay. And here, let me draw one imaginary line which joins these three spheres. We define this as A, B, and C. And now, we calculate the relationship between the edge length and the radius of sphere. Okay, that is the relationship between A and R in FCC in itself. And since here the edge length we already considered that as an A, this is the edge length, these are the edge lengths. So let me define this as an A edge length, and radius of sphere we defined that as an R. So here this is the radius of first sphere R, and this is the diameter of the second sphere. So radius is R, so diameter is defined as 2R, and this is the radius of third sphere, there is the R. So here the distance from here to here, this is the radius of first sphere R. So this distance is the diameter of second sphere, is defined as R plus R 2R, and this is the radius of third sphere. Now, to calculate the relationship between A and R, let me consider a triangle ABC. So let's consider a triangle ABC in which the angle C is equals to 90 degree. This is the angle C is equals to 90 degree. And since according to Pythagoras Theorem, we know that for a right angle triangle, the opposite to that right angle, so that is called as an hypotenuse, and the squares of the hypotenuse is equal to sum of the squares of the other two sides. And therefore, one can write according to Pythagoras Theorem, the AB square is equals to AC square plus BC square. Now, since AB square is equals to AC is nothing but it is the edge length of this unit itself. So edge length we already considered that as an A. So therefore AC is A. So AC square is A square plus BC is also an edge length of that cube. So it is also A square. So therefore A square plus A square is equals to 2A square. Now since AB is the hypotenuse, there is the imaginary line what we drawn here. So that joins all the three spheres. So the length of this face diagonal, this is called the face diagonal. So the length of this face diagonal is the sum of the radius of these three spheres. So here, this is the length you can calculate. This is the R plus 2R plus R. This is the R plus 2R plus R. That is equals to 2A square. So R plus 2R plus R is equals to 4R. 4R is equals to 2A square, or we can write the 4R by 2 is equals to A square. And let me simplify here only, friends. So A is equals to A square equal to 4R by 2. Therefore A is equals to, it is root of 4R divided by 2. So that is equals to root 4 wait. So this is the square. So just the mistake one here. So AB is this one. So this is the AB square. This is also AB square. Okay. So here, let me see. Okay. So this is 4r whole square. 4r whole square means 4 square, and is 16, and this is r square is equals to 2a square, or let me write this, a square is equals to 16 r square divided by 2, or a is equals to, so root of 16 r square by 2, that is equals to 4r by root 2. Okay. So 4r by root 2 is the a value. Okay. Or we also write this 4r by root 2 as 2 root 2 into r. Okay. So let me show you how we wrote this 4r by root 2 as in a 2 root 2 here. So this is a 4 by root 2 can written as 2 into 2 divided by root 2. Okay, so 2 as it is, let me write this 2 as root 2 into root 2 divided by root 2. Okay, 4 I am writing 2 into 2, and denominator root 2 as it is, 2 as it is. So this 2 is written as root 2 into root 2 because root 2 into root is again 2. So this root 2 cancels. So that is equals to 2 root 2. Okay, so 4 by root 2 is written as 2 root 2. Okay. You can write directly. And so this is the relationship between edge length and the radius of sphere. Okay. Is the A is equals to 2 root 2. Now, let me calculate the packing efficiency. Packing efficiency in face center cubic cell. Okay. This is equals to, we know the formula, that is the volume of all the particles in unit cell divided by volume of unit cell into 100. Therefore, packing efficiency, before I calculate the packing efficiency, let me calculate the volume of unit cell and the volume of all the particles. So first, let me calculate the denominator term, volume of unit cell. We know the volume of unit cell is A cube because the edge length is A for a cube. The volume of unit cell is A cube. Now, we have substitute the A value as 2 root 2. So it is 2 root 2 into R whole cube. So that is equals to 2 whole cube is 8. And since root 2 whole cube is root 2 into root 2 into root 2, that is 2 root 2, and R whole cube is R cube. So that is equals to A to the 16 root 2 into R cube. Okay. So that is the volume of unit cell in terms of radius of a sphere. Okay. Next, the second one is the volume of all the particles. Volume of all particles in FCC unit cell. Volume of all particles in unit cell, that is the FCC unit cell, is equals to, we know the formula, that is the number of particles is multiplied with volume of each sphere. That will give me the total volume of all the particles in the unit cell. So the number of particles in FCC unit cell is 4. The total number of particles we already calculated in FCC unit cell is 4, and volume of each sphere, we know volume of sphere is defined as 4 by 3 by R cube. So that is equals to 4 4s 16 by 3 by R cube. And so this is the numerator term, that is the volume of all the particles. Now substitute these two in the above equation. That is the volume of unit cell and volume of all the particles in the unit cell and calculate the packing efficiency. Therefore, packing efficiency is equals to, okay, numerator it is 16 by 3 pi r cube divided by volume of unit cell is 16 root 2 into r cube is multiplied with 100. So here r cube cancels, 16 it cancelled, and remaining is in numerator pi remains, in denominator 3 root 2 into 100. Now the value of pi is 3.142 divided by 3 into root 2 value, we know 1.414 is multiplied with 100. After simplifying that, you will get the packing efficiency is equals to 74%. Okay. So 74% is the packing efficiency in FCC unit cell. That means the total space occupied by the particles in FCC unit cell is equals to 74%. Okay. This is also very important. It is asked many times in your annual exam for 3 marks. So they may ask calculate the packing efficiency in FCC unit cell or calculate the packing efficiency in hexagonal closed packing structures or the packing efficiency in CCP structures, that is cubic closed packed structures, and the derivation is same for all the 3 types of these structures. Okay, so again let me repeat this. Packing efficiency in FCC unit cell. So here, first step is you have to consider the edge length of unit cell as A and the radius of sphere as R. Then calculate the relationship between the A and R. To calculate that relationship between A and R, you have to know how arrangement of the particles in FCC unit cell, how the particles are arranged. So in FCC unit cell, the diagonally opposite corner particles and face center particles are in touch with each other. You also write that word that in FCC unit cell, diagonally opposite corner particles and face center particles are in touch with each other. Therefore, we can draw this, or we can draw this structure. Okay. Then, to calculate that relationship, we have considered a triangle, that is the ABC, where angle C is equals to 90 degree. By using Pythagoras Theorem, we calculated the relationship between the A and R just by simplifying all these things. So just practice these things. Okay. So here, according to the Pythagoras Theorem, it is AB square equal to AC square plus BC square, where AC and BC have the edge lengths. So we have substituted edge length as A. So A square plus A square is 2A square. AB square, we calculated this face diagonal, length of this face diagonal in terms of radius of sphere, that is R plus 2R plus R whole square, that is 4R whole square. After simplifying, we get A is equals to 2 root 2 into R. Then use the formula to calculate the packing efficiency. PE is equals to volume of all the particles in unit cell divided by volume of unit cell into 100. Then calculate the denominator term first, that is the volume of unit cell. Volume of unit cell equal to A cube. Okay. So because A cube, it is because this is in a cube and the edge length is defined as A. So therefore the volume is A cube. Then substitute this A value from this equation. So that is A equal to 2 root 2. So here A is 2 root 2. So cubing this, we get 16 root 2 R cube. Then calculate the numerator term in PE, that is the volume of all the particles in FCC unit cell. That is the number of particles is multiplied with volume of each sphere. The total number of particles here is 4. So volume of each sphere is 4 by 3 pi r cube. So it gives 16 by 3 pi r cube. Now substitute these two values in above equation. Either you can define this as equation 1, and here you may write equation 1 implies. So PE is equals to, so in numerator it is 16 by 3 pi r cube. In denominator we calculated 16 by 2 pi r cube. After simplifying this, finally we get the packing efficiency is equals to 74%. This is the total space occupied by the particles in FCC in itself. Okay, next is the another one type of the packing. Students, the next one is the body packing efficiency in body centered cubic cell. Let me consider here the edge length as A and radius of sphere as R. Before I calculate the packing efficiency in BCC unit cell, let me explain you the arrangement of the constituent particles or the arrangement of the particles in the BCC unit cell. In BCC unit cell, we know there are 9 lattice points in which 8 corner particles and 1 is present at the center of the cube. So here the diagonally opposite corner particles and body centered particles are in touch with each other. Okay. So this is the unit cell, this is the cube. So here the particle which is present at the center of this cube, and these are the two diagonally opposite corner particles. So these diagonally opposite corner particles, they are in touch with each other. Okay. So this is the arrangement of the particles like that. The diagonally opposite corner particles, they are in touch with the body centered particles. So these two particles are in touch with the centered body centered, and also diagonally opposite these two particles also in touch with that centered particle. Now let me derive the relationship between the edge length and radius of sphere. And for that, let me draw the two imaginary lines. So the one which joins these three spheres. So we define this as A and B, and I will draw another one imaginary line. So on this face, so here this is the another one imaginary line. So let me define that as an T. Okay, sorry. Let me define this as C. Then here as an T. So to derive the relationship between these two, let me consider the two triangles. So first we consider the triangle here. This is BCD. So BC and D. And since here the angle D is equals to 90 degree. So here the angle D is equals to 90 degree. Now according to the Pythagoras Theorem, we can write BC square is equals to CD square plus BD square. Okay. This is BC square equal to CD square plus BD square. Now CD we know this is the edge length, and also BD or DB is also an edge length. Okay. And edge length we are going to consider that as an A. So it's A square plus A square. So that is equals to 2A square. Okay. So now BC square is equals to 2A square. Now let me take another one triangle. Let triangle the one A, B and C. Okay. Let me highlight this. This is the triangle. Another one I'm considering. This is A, B and C. So in triangle ABC, and here since the angle C is equals to 90 degree. Okay. So angle C is the 90 degree. So therefore opposite to this is the 90 degree. Okay, opposite to this right angle triangle, which is called a hypotenuse. So hypotenuse here is AB. AB square is equals to BC square plus AC square. Now since BC square, just now calculated, BC square is 2A square plus AC square is H length. So H length is defined as A. So this is the A and A square. So therefore AB square is equals to 2A square plus A square is 3A square. And since AB square, AB is the length of this body diagonal, let me express this length of a body diagonal in terms of the radius of sphere. So this is the R, radius of first sphere. This is the 2R, that is the diameter of the second sphere, and this is the R, this is the radius of third sphere. Therefore, the AB is length of body diagonal is, it is the sum of radius of these three spheres. So there is R plus 2R, so there is 4R. So 4R whole square is equals to 3A square. Therefore 4, let me write A square equal to this one as 4R whole square divided by 3, or in A is equals to, in numerator it is 4R, in denominator is root 3. Okay. So A square equal to 4R whole square by 3, taking square root on both the sides, so square and square root and square here it cancels, it is an A, and here square and square root it cancels 4R, and denominator remains as square root 3. So this is the relationship between the edge length and the radius of sphere. Now, after deriving the relationship between these two, let me calculate the packing efficiency. The packing efficiency in short we call that as an P dot E, that is equals to, we know the formula, that is the volume of all the particles in BCC unit cell is divided by, or in a unit cell divided by volume of unit cell is multiplied with 100. That's sense here. First let me calculate the volume of an unit. Volume of unit cell. First let me calculate that volume of unit cell is equals to. So volume of unit cell we define that as the number of particles present in that unit cell is multiplied with a volume of each sphere. Okay. So here we write that as volume of particles. So particles present in the unit cell, and here the unit cell is a BCC unit cell. BCC unit cell, therefore the total number of particles, not volume, it is the number of particles in BCC is multiplied with the volume of each sphere. That will give me the total volume of all the particles in BCC unit cell. So volume of unit cell is the volume of all the particles in unit cell. So in numerator term, volume of all particles in BCC unit cell. So there is a total number of particles in BCC unit cell multiplied with volume of each sphere. It will give me the total volume of all the particles in the unit cell. So total number of particles in BCC unit cell, we know there are 2, and it is multiplied with volume of each sphere. Each sphere volume is 4 by 3 pi r cube. Okay, 4 by 3 pi r cube is the volume of each sphere. So that is equals to 4 to the 8 8 by 3 by r cube. And next friends, the denominator term here is volume of unit cell. Volume of unit cell is equals to, okay, so here unit cell is in a cube, so we know the volume of cube is length into breadth into height as a cube, because length, breadth and heights they are defined as a, so a into a is equals to a cube. Now that is equals to, and since just now we derived the relationship between the edge length and the radius of sphere, a is equals to 4r by root 3. So therefore, we substitute here, this is 4r by root 3 whole cube. Find the cube of this, 4r by root 3. So 4 cube is 4 into 4 into 4, 64 r as r cube, and root 3 whole cube is root 3 into root 3 into root 3. So root 3 into root 3 is 3. So 3 is 3 into 3 into root 3. So root 3 into root 3 is 3. So root 3 as it is. So therefore it is 3 root 3. Now this is the denominator term. That is the volume of the unit cell. Now let me substitute these two in the above equation. Let me define this as equation 1. Okay. Substituting these two in above equation. Okay. This the one is the volume of all the particles, and another one is the volume of unit cell in terms of radius of sphere. Therefore, packing efficiency is equals to, packing efficiency is 8 by 3 pi r cube divided by 64 by 3 root 3 into r cube. Let me cancel the terms r cube here, and 8 ones are, it is 64, 3 and 3 get cancelled, so here to multiply with 100, so that's, now the remaining terms are, first one is the pi value is 3.142, so divided, and this root 3 goes to numerator, so into root 3 divided by, in denominator term only 8 remains, so 8 into 100. So considers the packing efficiency is equals to 3.142 into root 3 divided by 8 into 100, that is equals to 68%. Okay. Just simplify that and calculate, so you'll get 68. So this is the percentage of the total space occupied by the particles in a BCC unit cell. Okay, let me again revise this. So the packing efficiency in BCC unit cell is, so to calculate the packing efficiency, first consider the edge lengths and radius of an atom as r and the edge length of unit cell as an a. Then find the relationship between the edge length and radius of a sphere or atom. Then for that, consider the two triangles. Okay, the first one is the BCD. So this is the BCD triangle. So here BC is the hypotenuse. So therefore, according to Pythagoras Theorem, BC square equal to CD square and BD square. Substitute these CD square and BD square values, you get 2 square. Then consider triangle ABC. So in this triangle, AB is the hypotenuse. So this is the right angle triangle. So therefore, AB square is equals to, you get 3 square. So AB is the length of body diagonal expressed that in terms of radius of sphere, there is a 4r. So AB is this is the length of body diagonal r plus 2r plus r is a 4r. So then find the A equal to 4r by root 3. Then the packing efficiency formula is volume of all the particles in BCC unit cell divided by volume of each unit cell. Then individually calculate the numerator term and the denominator term as volume of all the particles in BCC unit cell using this formula, and volume of unit cell is defined as A cube. So we got two numericals, these terms. So then substitute these two in the above formula, you will get the final answer. That is the packing efficiency in BCC is equals to 68%.